Hello dear students, this is our sixth lecture for our course. Some discrete probability distributions. No matter whether a discrete probability distribution is represented graphically by a histogram in a tabular form or by means of a formula, the behavior of a random variable is described. Often, the observations generated by different statistical experiments have the same general type of behavior. Discrete random variables associated with this or these experiments can be described by essentially the same probability distribution and therefore can be represented by a single formula. In fact, one needs only a handful of important probability distributions to describe many of the discrete random variables encountered in practice. Such a handful of distributions describe several real-life random phenomena. For instance, in a study involving testing the effectiveness of new drug, the number of cured patients among all the patients who use the drug approximately follows a binomial distribution. In an industrial example, when a sample of items selected from a batch of production is tested, the number of defective items in the same usually can be modeled as a hypergeometric random variable. In a statistical quality control problem, the experimenter will signal a shift of the process mean when observational data exceed certain limits. The number of samples required to produce a false alarm follows a geometric distribution, which is a special case of the negative binomial distribution. On the other hand, the number of white cells from a fixed amount of an individual's blood sample is usually random and may be described by a Poisson distribution. In this chapter, we present these commonly used distributions with various examples. The first distribution is binomial and multinomial distributions. An experiment often consists of repeated trials, each with two possible outcomes that may be labeled success or failure. The most obvious of applications deals with the testing of items as they come off an assembly line, where each trial may indicate a defective or non-defective item. We may choose to define either outcome as a success. The process is referred to as a Bernoulli process. Each trial is called a Bernoulli trial. Observe, for example, if one were drawing cards from a deck, the probabilities for repeated trials change if the cards are not replaced. That is, the probability of selecting a heart on the first draw is 1/4, but on the second draw it is conditional probability having a value of 13/51 or 12/51, depending on whether heart appeared on the first draw. This then would no longer be considered a set of Bernoulli trials. The Bernoulli process. Strictly speaking, the Bernoulli process must possess the following properties. The experiment consists of repeated trials. Second, each trial results in an outcome that may be classified as a success or failure. Number 3, the probability of success denoted by B remains constant from trial to trial. Number 4, the repeated trials are independent. Consider the set of Bernoulli trials where 3 items are selected at random from a manufacturing process, inspected and classified as defective or non-defective. A defective item is designated a success. The number of success is a random variable x, assuming integral values from 0 through 3, the 8 possible outcomes, and the corresponding values of x are as in the following table. Since the items are selected independently and we assume that the process produces 25% defectives, we have the probability of n dn equal to probability of n times the probability of d times the probability of n, where the probability of n is the probability of non-defective, the probability of d is the probability of defective, which is equal to 3 over 4 times 1 over 4 times 3 over 4, which is equal to 9 over 64. Similar calculations yield the probabilities for the other possible outcomes. The probability distribution of x is therefore x equals 0, 1, 2, 3, and the function of x, or the probability of x, equal 27 over 64, 27 over 64, 9 over 64, 1 over 64 respectively. Binomial distribution. The number x of successes in n Bernoulli trials is called a binomial random variable. The probability distribution of this discrete random variable is called the binomial distribution, and its values will be denoted by bx and n and b, since they depend on the number of trials and the probability of a success on a given trial. Thus, for the probability distribution of x, the number of defectives is probability of x equal 9 over 64. Let us now generalize the above illustration to yield a formula for b, n, and b. That is, we wish to find a formula that gives the probability of x successes in n trials for binomial experiment. First, consider the probability of x success and n minus x failures in a specified order. Since the trials are independent, we can multiply all the probabilities corresponding to the different outcomes. Each success occurs with probability b and each failure with probability q equal 1 minus b. Therefore, the probability for the specified order is b with bar x times q with bar n minus x. We must now determine the total number of sample points in the experiment that have x successes and n minus x failures. This number is equal to the number of partitions of n outcomes into 2 groups, with x in one group and n minus x in the other, and is written as n combination x as introduced in section 2.3. Because these partitions are mutually exclusive, we add the probabilities of all the different partitions to obtain the general formula, or simply multiply b with bar x times q with bar n minus x by n combination x. The binomial distribution, a Bernoulli trial can result in a success with probability b and a failure with probability q equal 1 minus b. Then the probability distribution of the binomial random variable x the number of successes in n independent trials is equal to n combination x times b with power x times q with power n minus x, which x equal 0, 1, 2 until n. Note that when n equals 3 and b equal 1 over 4, the probability distribution of x, the number of defectives, may be written as 3 combination x times 1 over 4 with power x times 3 over 4 with power 3 minus x, and x is equal to 0, 1, 2, 3, rather than in the tabular form on page 144. Example: the probability that a certain kind of component will survive a shock test is 3 over 4. Find the probability that exactly 2 of the next 4 components tested survive, assuming that the tests are independent, and b equal to 3 over 4 for each of the 4 tests. We obtain the probability for 4 and 3 over 4 is equal to 4 combination 2, 3 over 2 times 3 over 2 with power 2 times 1 over 4 with power 2, which is equal to 27 over 128. Where does the name of binomial come from? The binomial distribution derives its name from the fact that n plus 1 terms in the binomial expansion of q plus b with power n correspond to the various values of b for x equal 0, 1, 2 until n. That is, q plus b with power n equal to n combination 0 times q with power n plus n combination 1 times b times q with power n minus 1 plus n combination 2 times b with power 2 q with power n minus 2 plus and so on until n combination n times b with power n. Since b plus q equal 1, we see that summation from x equal 0 until n for b of x n b equal to 1. A condition that must hold for any probability distribution. Frequently we are interested in problems where it is necessary to find probability of x less than r, or probability of x is between and equal a and b. The binomial sums is equal to summation from x equal 0 to r for b of x n and b are given in table A1 of the appendix for n equal 1, 2 until 20 for selected values of b from 0.1 to 0.9. We illustrate the use of table with the following example. The probability that a patient recovers from a rare blood disease is 0.4 if 15 people are known to have contracted this disease. What is the probability that A, at least 10 survive? Number B, from 3 to 8 survive, and number C, exactly 5 survive. Number A, let x be the number of people who survive. The probability of x is greater than or equal 10, which is equal to 1 minus probability less than 10, which is equal to 1 minus summation for probabilities of x equal 0 plus probability of x equal 1 plus probability of x equal 2, x equal 3, x equal 4, x equal 5 until x equal 9, which is equal to 1 minus 0.9662, which is equal to 0.0338. Number B, probability of x is between or equal 3 and 8. which is equal to the summation of probabilities from probability of x equals 3 plus probability x equal to 4 plus probability x equal 5 plus probability of x equal 6 plus probability of x equal 7 plus probability of x equal 8, which is equal to 0.8779. Number C, probability of x equal 5, which is equal to 0.1859. Another example, a large chain retailer purchases a certain kind of electronic device from a manufacturer. The manufacturer indicates that the defective rate of the device is 3%. The inspector randomly picks 20 items from a shipment. What is the probability that there will be at least one defective item among these 20? Suppose that the retailer receives 10 shipments in a month and the inspector randomly tests 20 devices per shipment. What is the probability that there will be exactly 3 shipments, each containing at least one defective device among the 20 that are selected and tested from the shipment? The solution, number A, denote by X the number of defective devices among the 20, then X follows B or binomial 20 and 0.03 distribution. Hence, probability of X greater than or equal 1 equal to 1 minus probability of X equal 0, which is equal to 1 minus probability of 0, 20 and 0.03, which is equal to 1 minus 0.03 with power 0 times 1 minus 0.03 with power 20 minus 0, which is equal to 0.4562. Number B, in this case, each shipment can either contain at least one defective item or not. Hence, testing of each shipment can be viewed as Bernoulli trial with B equal 0.4562 from part A, assuming that the independence from shipment to shipment, and denoting by Y the number of shipments containing at least one defective item. Y follows another binomial distribution, binomial for 10 and 0.4562. Therefore, probability of Y equals 3 is equal to 0.1602. The areas of application from the examples 5.1 through 5.3, it should be clear that the binomial distribution finds application in many scientific fields. An industrial engineer is keenly interested in the proportion defective in an industrial process. Often quality control measures and sampling schemes for processes are based on the binomial distribution. This distribution applies to any industrial situation where an outcome of a process is discussed and the results of the process are independent, with the probability of success being constant from trial to trial. Thank you, and continue in the next lecture.